everyone. So in the last class what we did, we installed a gripper at the end of this robot and we saw it requires a tool calibration. So we could successfully calibrate the origin of the tool. Okay, I saw you different methods how it can be done. Okay, so in today's class we'll move ahead further in tool calibration. As we discussed in the last class, it requires two different things to be done. First is the orientation calibration and next one is the tool end effector frame calibration that actually shows the origin to the controller. Got it? So two different types of calibration are there as far as tool is concerned. I'll just show you the representative image that clearly shows tip of the tool. One corner I have marked it, and you see now I can locate precisely this tool to any reference mark which is there in the workspace of the robot. I can take my robot to exactly to that point because that origin is now known. But now I want to orient the robot as well with reference to that particular, okay, that TCP origin. Okay, so that is what we are going to do today. So let me just move further, and yes, so it is the orientation of the tool frame with respect to the robot's tool flange. Okay, tool flange is something over here where you actually attach your tool. Okay, so this is what is TCP orientation calibration. So that will intend to find out the transformation matrix from here to this TCP that clearly says the rotation along three different axes, and it takes me to the aligned orientation with respect to the base to this tip. Okay, so that is what is orientation calibration. So yes, this allows precise estimation and or control the end effector tool orientation with respect to the robot base. So with respect to the robot base, which is here, now I can also orient my end effector with respect to the tip of this tool. So tip can be made stationary and whole of the end effector can now rotate about that. Okay, so that tip will remain stationary. So after the completion of orientation calibration, we should expect our robot to do that. Okay, so the TCP orientation is calibrated after TCP origin calibration. That is, we want to know this origin first. Okay, first we'll translate from this flange till this location, and then I'll orient the frame so that it aligns with the tool orientation. Got it? So this is the job that we want to do. So there are two approaches for TCP orientation calibration that use existing world frame as the reference. So these are the two methods. We'll talk about this that uses world frame as a reference. So what is the world frame? It is the frame which is attached to the workspace, anywhere in the workspace where your robot is standing. If it is just a single robot, the world frame can be placed at the base of the robot. So it is exactly the zero frame of the robot itself. That also can be done. So yes, so this frame now is a free frame about which I want to understand how my tip of the TCP is oriented. Okay, so that is what is our job. So these are the two methods that uses world frame, and the next method is a 2-point method for TCP orientation calibration. So let us begin with one of them, 5D method to begin with. So what it says, it uses the world frame. So now you see this is the reference frame. This is your robot's base frame. Both are parallel to each other, you see. They are just translated by some distance along X, Y and Z, but both of them are parallel to each other. Now the tool frame is this one. Okay, so what are the steps? The axis of the tool frame is aligned parallel to the axis of the world frame using manual jogging. You jog till this one of the axis, that is the tool frame axis. I call it as Z axis, normally the tool axis. Different robot manufacturers do assign different axes to the tool. I prefer it putting Z axis along the tool axis. So if it approaches, it will approach along that direction. If it goes away, it will go away along that direction. this communicates the tool orientation to the robot controller. Now I will record whatever is the orientation of this flange with respect to this and this tool, how it is oriented. So whatever is this orientation, this becomes the orientation of my tool with respect to the flange. So using this, this as a reference, okay, I understand, okay, Z is aligned with Z. So I leave controller to decide upon X and Y directions. Okay, so with this, whole of this is now totally constrained and it is fully known. Okay, once this is fully known, this frame is automatically known by using the robot's forward kinematics. So from here to here, that transformation is identified by the controller and that is saved as a tool frame orientation with respect to the robot flange frame. Got it? So this is how it works inside. So the tool orientation, that is the ZT is for tool Z. Okay, axis of the tool is aligned to the Z axis of the world frame. Okay, the axis XT and YT, that is the tool axis, are automatically assigned by the controller, and it is not much significant here because I should be very happy with the Z axis only. There are many applications which are here to use that particular kind of calibration here. Few of them are welding operation. You know, welding can be done just by reaching to a point. Okay, you can just reach there and you can do it. It is irrelevant if you rotate along the axis. So whatever is the axis rotation of the tool axis rotation is not very much relevant here. Okay, so however you align, it is all the same. Same with laser cutting. So rotation along the axis of laser line is irrelevant. It will cut along the same path, same direction, same position. So again, water jet cutting or painting also, you rotate your tool, paint spray will go in a similar manner. Okay, milling, grinding, 3D printing. So all these operations can use this kind of calibration. Okay. Why it is 5-day? Because rotation about Z axis is allowed. Rest everything is constrained. So rotation of Z axis, that means out of the 6 constraints that you can put in this tool frame, only one motion is allowed. Rest everything gets constrained. So this is allowed. You can rotate the tool about the axis. That is, X and Y can have any position with respect to the Z axis. So that means this rotation is allowed, and that is known as the 5D method of calibration, where these two are aligned. Okay, so let us look 6D method now. Here we are perfectly aligning all the axes. Okay, so all the axes of the tool frame are aligned parallel to the axis of the world frame using manual jogging. Okay, so you have aligned Z axis to the Z axis of the world frame. Okay, so and also you have aligned X to this X, Y to this Y, directions are different. Okay, so now whole of the tool frame is constrained. It is locked with the world frame. Once you define, you align, it is fully locked. Got it? So that is why it is a 6D method. You have locked everything now. Got it? You have already defined the origin, and now you have defined all the axes of the frame. That means you are fully locked. So it is a 6D method. So how they are placed is something like this. So you see, Z axis is parallel to minus Z of the world frame. X axis is parallel to the X axis of the world. Y axis is parallel to minus Y of the world frame. Okay, this is how you have to align through manual jogging only. So this effectively is rotation of the tool frame about X axis by an angle 180 degrees. So you see, this system of tool frame is actually, if you rotate world frame about X axis by 180 degree, you will get to this frame. Got it? So this is the effective transformation that is there. Okay, and now let us do some analysis on this and understand how internally it is doing all the calculation, what data is finally saved to the controller so that it gets to know the orientation of TCP with respect to the flange. Okay. So yes, there are many applications now. Few of them are 5D jobs. All the jobs which are 5D in nature, like welding job, laser cutting job, all those jobs can be done with 6D method of calibration also. Apart from that, pick and place task or pelletizing task, assembly task, these tasks specifically require 6D kind of calibration. So it is 6D because all the motions are defined and it is constrained and it is controlled also. Okay, so what the robot controller does inside, once you align it, how it finds out the transformation from here to here. Your reference frame with respect to the base, okay, is same as base with respect to the base, that is I3. There is no rotation about any of the axis. So this is what can be written very well. So transformation of reference with respect to the base is equal to I3, that is this matrix 1 1 1 0 0 0 0 0 0. Okay, so this is your I3 matrix. Okay, now base to the flange, from here to here, that transformation is evaluated using forward kinematics. So forward kinematics, what does it have? It has position of this as well as orientation. That is the, if you see the forward kinematic transformation matrix, so this is your base to the flange transformation. This is your end effector position. Okay, this is 1, these 3 are 0. This is your transformation. So this is already there in your forward kinematics transformation matrix. So you extract it directly from there. You know the joint angles, you know the DS parameters of your system. So this can be very well known. Okay, done. Next, upon aligning the TCP to the reference frame, what you saw, it is effectively rotation about x-axis by 180 degree. That means this is now rotated about x-axis by an angle 180 degree. So now how is your TCP oriented? Basically TCP with respect to the base is rotation about x-axis by an angle 180 degree. Cos, sine, minus sine, cos. This makes it exactly this. So this is your BQT, that is transformation of tool frame with respect to the base. This is now known. Okay. So now let us come back to your 5D method. So once you align this, so you didn't bother whatever orientation you are aligning to your tool frame. So you have made your tool frame in whatever way. Okay, so you have aligned. So whatever is the position of your tool with respect to this reference, okay, so it will automatically assign x and y like this, and it will take those data and it will save it. So it won't let you know that it has placed x and y exactly like this, but yes, internally it does it similar way. So now coming back to this, so now B to T, that is transformation, that is the rotation matrix of the tool with respect to the base. Tool with respect to the base is base to flange and flange to tool orientation. Okay, and also any inverse of the rotation matrix is equal to transpose of the rotation matrix. So these two things should be noted. So moving ahead, so the identified TCP orientation with respect to the flange now will be, so if you say flange to the tool, so you just have to bring this one to this side taking inverse, and you are remaining with flange to the tool, that is here. Okay, so it becomes this. Got it? So what was this? Base to flange transpose or inverse. Base to flange, that matrix is known. Okay, and base to tool tool is here, that is also known. You just copy it here, and using these two you got to know what is flange to the tool. So this is what is the orientation matrix we were interested in, and it can quickly now find out. The controller can do it, okay, by using this calculation. Got it? So this method is very quick. You can quickly align, you can do it, but because it is a manual alignment, it is not very precise. You have to depend on your eye estimation when you do it. So you are manually aligning it by some jogging method. So it may not be very precise, but yes, it is quite good for quite number of applications like pick and place using two-fingered gripper. Little bit of half a degree here and there is okay. Okay, still you can hold your object. Okay, now let us do a different method which is more precise. It is known as a two-point method for TCP orientation calibration. Okay, so it is performed immediately after TCP origin calibration. Now you already know the origin of the tool center point. So if this is the image, so the marked point which is making contact with the reference point, that is the origin. Okay, now I have to find out the orientation. That's something that we did just last slide. Last two methods, we want to find out the same matrix. Okay, so now how to do it, how to use this method? By jogging the tool, the external reference point is brushed to the calibrated TCP origin. Okay, so external reference point, you have to bring it closer to the, almost like touching to the TCP origin. Okay, external reference point, and this should match. A point on z-axis is taken. Okay, and you also will have to brush the reference point to a point on the z-axis and a point on the xz plane of the tool by gradually jogging the tool. So 3 points that you have to locate. First, TCP, that is the TCP origin, should brush against the reference point. Next, you have to brush the reference point to one of the point on the along the z-axis that you want to make it, and another point which is on somewhere on xz plane. Okay, using these 3 information, it calculates the unit vectors. Those are aligned along the TCP frame axes. Okay, so that is what will be found out. Okay, so using this procedure, the z-axis is actually assigned by the user itself, where x and y is automatically calculated by the controller with the 2 points that additionally you have made contact with the reference point, that is a point on the xz plane of the tool and the known point TCP position, that is TCP origin. Okay, so how it does it, let us come to that. So the first step, what we did, the TCP is moved to any arbitrary point, this point, that is the tip of this reference point. So that point is contacted with the origin of your TCP. This records the position vector or simply the position of the reference point R with respect to the robot base. How it does it, let us just look at. Okay, you made a contact over here. Got it? This point. Okay, so robot already knew this location. Using forward kinematics, it will quickly calculate the location of this flange. So it has this information, that is the tool flange with respect to the origin, that is obtained using forward kinematics. And because this is a origin calibrated tool for which you have already done the origin calibration, you also know this location with respect to this, that is the TCP X, TCP Y, TCP Z are known. That means this vector is known with respect to this, that means T is known. So finally R, this R vector is calculated using F plus T. So now you know the location of your position vector of your tip of the reference tool. Okay, so now I know the location of this in the frame, robot base frame. because you are doing forward kinematics over here. So with respect to that, this vector is known. First job done. Then your second job, the TCP is now moved so that the reference point is brushed to a point on the ZT axis. Any line along the line where you want to make it as a Z axis, you have to brush it against one such point on the tool. Okay. First you contacted here. Second point is here. Okay. Where you are brushing your reference tool to that particular point which has a negative value. You took it backwards. Why? I will tell you. Because the negative value of ZT commonly lies on the tool itself. So it is easy to locate. Okay, and hence it is more convenient. So what you did is something like this. You made contact somewhere here. So now again TE is known. That is the end effector of the tool. Position is known. Why? Because it is a calibrated tool and using forward kinematics you have this information. Okay, forward kinematics you can calculate this. This was a known TCP, so T was known. So finally you know what is your this vector. TE vector is known. So this is known. Okay, so this is the first job that you do when you make contact over here. Okay, as soon as you make contact over here, this is the first job you do. Okay, now the vector along ZT, that is the W vector, which is marked as shown in this figure, is basically how much is that? W is equal to TE minus R, because you know W plus R is equal to TE. So just by playing with vector sum you can find out this vector, that is W. And where is this oriented? Aligned. It is aligned along the ZT, tool Z axis. Okay, so now you can calculate unit vector ZT along W. ZT, that is the tool Z, is this W by magnitude of W. So it is unit vector along Z axis of the tool. First thing that is found out. Step 2. Now next what you did, the TCP is moved to brush the reference point to any point on XZ plane, any point on the XZ plane of the tool. So this is your XZ plane, the plane which is formed by this. So this is your XZ plane. You can see this. So this is your plane. So you have to make contact anywhere on this plane. So how it is easy to do? You can take comfortably one of the point in XZ plane as a which is lying on the tool itself. It is easy to make that reference. Okay, so conveniently I place it on the other gripper finger, okay, which is lying along the x-axis. I want to make that as an x-axis somewhere along that. So not exactly on x-axis it will be, it may be somewhere on the XZ plane. So approximately I placed it here. Maybe it is little different because of little bit of misalignment of the two fingers. It may not be exactly along x-axis, two tips. It can be little like this. Okay, so that is the region. Okay, so what effectively it does now. So this was your ZT, that is you have calculated in the earlier step, and U vector is R minus T. So now again tool tip is known using forward kinematics, and this T vector you calculated the tool tip vector. Okay, so that is using the known tool tip, that is here. How much is your R? R is also known because your reference vector is always known with respect to this. Okay, so R minus T gives you U. U is a vector that lies somewhere near to your x-axis of the tool, but it is on the ZX plane. Okay, approximately it will be on somewhere near to x-axis, but not necessarily that. So it will be on the ZX plane. Okay, so the vector along Y T axis, tool Y axis is given by V, which is calculated as V is equal to W cross U. Okay. So U vector is in ZX plane, and you already have Z vector. So cross product of those two will give you a vector which is perpendicular to the ZX plane. Okay. Perpendicular to the ZX plane, any vector will be parallel to YT. Okay. That will be parallel to YT. So now I'll use V to find out YT. That is the tool Y axis. So how is that calculated? V by magnitude of V, that gives you a unit vector parallel to YT. Okay, so that is there. So this is how YT is calculated. We calculated ZT in the previous step. In this step, you have calculated YT. So XT can now be obtained precisely. U was not along XT. Okay, so U was somewhere near to XT. It was on XZ plane. Okay, but now it is XT, which is taken as a cross product of Y and Z, will exactly give you the XT unit vector which is XT. Got it? You can see this equation clearly now. So yes, so this is what is obtained. So you have obtained XT, YT and ZT, all of them. So all the axis vectors XT, YT and ZT is now known in the robot's base frame. In this frame, all the vectors are known. So the orientation of TCP may now be written as 3×3 rotation matrix. You know, it is projection of tool frame along X, along Y, along Z. Similarly, tool frame Y along X, along Y, along Z. Tool frame Z along X, along Y, along Z. So it is nothing but your tool vector projections along X, Y and Z. So it is by the fundamentals that you have understood about the rotation matrix and effector rotation matrix, it is exactly this one. Okay, so you can quickly, whatever you have calculated, you can put it as XT along X, XT along Y, XT along Z. So that becomes the first column of this. Similarly, second column will be YT along X, YT along Y, YT along Z, or similarly this one. So this is your rotation matrix 0 to the tool frame. That is the tool frame expressed with respect to 0. So that is the complete transformation, now you know. And how much is that? It is 0 to flange, 0 to flange and flange to this. Two transformations are there. First one is here, okay. Second one is here, okay. So using those two, this can be obtained. What is already known to you, because you know XT, YT and ZT. So now I'll make use of that. So I'll make use of forward kinematics again. 0 to this is already known to you using forward kinematics. So this is known. Okay. So you can bring it again using inverse. So how much is flange to tool? That is this one. Flange to tool, it is inverse of this into this. 0 to tool is known. This is known using forward kinematics. So this is calculated. Okay, so again inverse is equal to transpose of the matrix. So this is there. So now 0 to F, you know it is obtained using forward kinematics. So this is calculated. So only assumption which is here is the orientation of the tool didn't change while jogging during the entire procedure. Okay, so tool frame should be kept, but one can make this algorithm, you can work on this, make it rugged against that also. But this could be one of the simplest approach, which can be called as a 2-point method. Okay, TCP origin was already known. you brushed at two additional points, that is this one and a point over here. Okay, so that is why it is there. Okay, so now there is yet another method, but that is, you cannot call it a method here because it is directly fed to the controller using the known data. Okay, if the tool is well known to you, you know it is having some shape which is very well known, and you also know the orientation of that, the precise location of your tip with the flange dimensions. You know where it is going to center with the flange, and also the tip where you want to work with. So if that vector, that orientation is well known, you can directly feed those data to the controller. The common sources are CAD. If you have a CAD design of your tool, even if it is a gripper or it is a welding tool, if you know CAD, you can very well know to a very good clarity that how is your tool tip oriented and located. Okay, through some external calibration tool like KUKA track, as we showed you, or there is a tool with ABB also, which is known as a bullseye. They do exactly same thing. It directly takes the data from the external calibration and feed it to the controller, or using any manufacturer's technical specification of the tool. If a tool is manufactured by any manufacturer, sometimes they do provide also how is my tool tip located with respect to the flange where you are going to place this. Okay, so exactly those information you may be having. Okay, so I'll show you some video demonstration now for this. What is the result of doing TCP calibration, that is the tool tip origin calibration and tool tip orientation calibration. So first video here will show you a motion in tool frame. So now it is moving along the tool centerline axis. It can be Z axis of the tool, and other two orthogonal axes also I'll be moving it, that is along X and along Y. Those are orthogonal to this Z axis. This is the second axis motion. These are the translation motion along the tool frame axis. This is yet another axis which is perpendicular to the both of them. So Z axis you have seen, that was the first one. Okay, so these were the three, and also I'll show you one more video which shows rotation about tool tip. Intentionally I have kept a reference so that you can understand that it is rotating about, that actually it is not rotating, it is trying to make a roll motion and the pitch motion about the tool axis. It will do that, it will come back. There is some error over here that is visible as a gap here, because you know these methods are manually calibrated. You cannot go very close to the reference point also. So now it is moving like a pitch motion along the tool. So now I'll do the Z-axis rotation about the tool axis itself. It almost rotates in the axis of the tool itself. So you see there is some misalignment, but yes, it is very closer to the Z-axis. This is what is the result of doing tool tip calibration, tool frame calibration. You find out the position, you find out the orientation, and that gives the additional capability for the robot to move it in Cartesian space, move the tool tip in the Cartesian space. So that's all. Thanks a lot. So in the next class, we'll start with the next module, that is calibration of the industrial robot systems, the things which are also there in the workspace. That is the object which is there. Okay, you have a fixed tool which is there in the workspace, your workpiece, your work surface. your turntable if it is there. So that also, the frames which are attached to those external objects should also be known to the robot, so that it can make movement with respect to that also. Okay, so that is your next module is all about. So that's all for this lecture. Thanks a lot.